This is section 8.2. Construct a frequency distributions for quantitative data, construct histograms, determine the shape of a distribution from a histogram, and construct a frequency polygram and ogives. Objective 1. A frequency distribution for quantitative data. To summarize quantitative data, we use a frequency distribution just like those for qualitative data. However, since these data have no natural categories, we divide the data into classes. Classes are intervals of equal width that cover all values that are observed in the data set. The lower class limit of a class is the smallest value that can appear in the class. Notice the lower classes are here, 0, 5, 10, and 15. The upper class limits of a class is the largest value that can appear in the class. Here are the upper class limits, 4, 9, 14, and 19. Notice the lower class limits go up and down, just like the upper class limits go up and down. We don't look at it from side to side. The first definition is the class width. You might want to make note of this formula. You can print out that formula sheet I have in Blackboard, and you can add formulas to it. The class width is the difference between consecutive lower class limits. See, right here it says the class width is 5 minus 0. Notice the width, again, is spanning up and down. So it's 5 minus 0, which is 5. I could also use the other two, 10 minus 5, which is 5. You're always going to get the same class width, no matter which two lower class limits you use. Guidelines for choosing classes. There are many ways to construct a frequency distribution, and they will differ depending on the classes chosen. Following our guidelines for choosing the classes. Every observation must fall into one of the classes. The classes must not overlap, the classes must be of equal width, and there must be no gaps between the classes. Even if there are no observations in a class, it must be included in the frequency distribution. So here are the steps. Step 1, choose a class width. Step 2, choose a lower class limit for the first class. This should be a convenient number that is slightly less than the minimum data value. So if the smallest value in the data is 5, maybe you would start with 0. If the smallest data value was 110, maybe you would start with 100. Step 3, compute the lower limit for the second class by adding the class width to the lower limit of the first class. The lower limit for the second class is equal to the lower limit for the first class plus the class width. Compute the lower limits for each of the remaining classes by adding the class width to the lower limit of the preceding class. Stop when the largest value is included in a class. Count the number of observations in each class and construct the frequency distribution. All right, so as an example, they give the emissions of 65 vehicles in units of grams of particles per gallon of fuel. They want you to construct a frequency distribution using a class width of 1. Notice all the data points, 1.5, 0.87, 1.12, 1.25, 3.46. They're all 2 places. So what they do is they search all of the data and they realize that 0.25 is the smallest value. So if I just click back here again, and as I'm searching, here I see it quickly, 0.25, but if I compare all the other numbers, the 0.25 is the smallest number. So what they do is they pick the lower limit to be 0 as the lower limit of the first class. The class width is 1, and the first lower limit is 0, so the next lower limit of the next class will be 1. So what they're doing is they're setting up that vertical line, which is, where is that slide? Right here. They're setting this up right here. This one has a class limit of 5, so it's 0, 5, 10, 15. If it went further, it'd be 15, 20, 25, 30, 35, etc., etc. But since this starting at 0 and they saying it has a class width of 1, they're adding 1 to all of them. They didn't show that they went 0 plus 1 to get the first one. But then they add 1 to all the remaining of them. And since the largest value is 6.64, every data value is now contained in the class, meaning that they're going up to 7 because they need to get at least a 6.64. Then they go over here and they set this up. Notice they're going 0 to 1, 1 to 2, to 3, to 4, to 5, to 6. That's what they just calculated, all of these values here. Now what they have to do is make sure all of the numbers are accounted for. So since this lower limit of the second class is 1, and all those data points were 2 decimal places, this has to go up to 0.99. If it was only 1 decimal place, you would go 0.9. If it was 3 decimal places, you'd do 0.999. But notice that the difference from here to here, this is also a 1. If I subtract 1.99 minus 0.99, I still get the class width of 1. So once you get these first set up, you can just pretty much add 1 to all of these upper limits, and that will set up. Now the way they get the frequency here is they literally looked through all of the data points and counted that there were 9. So, hold on a second. So if you look at, let's pick a smaller one so I don't have to go through 9 of them. Let's do this one here. They have a frequency of 3, and that's between 4 and 4.99. So if I go back to the data and I want to look for all of them that are between 4 and 4.99. So here's one right here. That's 4.04. And as I'm searching for the other ones, I know there's 3 because they already said there was 3. There's another one, 4.24, and here's another one, 4.58. So there's only 3 frequency points for the data between 4 and 4.99. So now I go back to the data that they set up with the frequency, and that's where they get all these numbers from. So there's 9 data points between 0 and 0.99. There's 26 data points between 1 and 1.99, etc., etc. So the next slide says, given the frequency distribution, a relative frequency distribution can be constructed by computing the relative frequency for each class. This is the next formula. I believe this one's on the sheet, but it says the relative frequency is the frequency value divided by the sum of all frequencies. So what they do for that is they add this all up. This right here is the summation symbol, and you add up all these frequencies. So on your calculator you add 9 plus 26 plus 11 plus 13 plus 3 plus 1 plus 2, and that's 65. I think in the original one they said there was 65. But to calculate the relative frequency, this very first one is going to be 9 divided by 65 on the calculator. So 3 decimal points make that 0.138. This one here is going to be 26 divided by 65, and that comes to 4.00. This one here is 11 divided by 65. That comes to 0.169. This one here is 13 divided by 65. So on the calculator, the 13 goes in first, divided by 65, 0.200. The 0.46 was going to be 3 divided by 65. And then the last two, 1 divided by 65 and 2 divided by 65. So that's the relative frequency. That's how you calculate that. And histogram. Once we have the frequency distribution or relative frequency distribution, we can put the information in graphical form by constructing a histogram. A histogram is constructed by drawing a rectangle for each class. The heights of the rectangles are equal to the frequencies or the relative frequencies, and the widths are equal to the class width. Notice they're touching in between the graphs. The frequency histogram and relative frequency histograms are given for a particular emissions data. Note that the two histograms have the same shape, The only difference is the scale on the vertical axis. So on this one here, we're plotting frequency, so 0, 5, 10, 15, 20, 25, 30. Where those numbers came from is back over here. It's going from 9, 26, 11, 13, 3, 1, and 2. So they're plotting that. So between all right, hold on. It's not going. There it goes. So between 0 and 0.99, there's 9. Between 1 and 1.99, there's 26. So let's go back down to this one. So between 0 and 0.99, there's 9. Notice it's approximately 9 right there. This goes up to 26, and these other ones will follow the other ones. Notice the relative frequency. Again, it comes from the same numbers, but it came from the division that we did. So this here, when you're between 0 and 0.99, you're going to be at 0.138. So that's here, 0.138, approximately right here. This is the next one, 0.38, or whatever that was. 0.4 was exactly. So that's at 0.4. Exactly. And so forth and so on. So they will have the same shape because one is the frequency and the other is the relative frequency. They are in line with each other. There are no hard and fast rules for choosing the number of classes. In general, it's a good idea to have more classes rather than fewer, but it's also good to have reasonably large frequencies in some of the classes. There are two principles that can guide you making the choice. Too few classes produces a histogram lacking in detail. Too many classes produces a histogram with too much detail so that the main features of the data are obscured. So looking at these two slides here, the following histograms illustrate too many classes and too few. Notice here, the jagged appearance distracts from the overall shape of the data. This is too many of them. And this one here is too few. Only the most basic features of the data are visible. There's some calculator keystrokes if you wanted to go through some of the calculator keystrokes on a TI-84 Plus. Open-ended classes. It is sometimes necessary for the first class to have no lower limit or for the last class to have no upper limits. Such a class is called open-ended. When a frequency distribution contains an open-ended class, a histogram cannot be drawn. Notice how this is here, 85 or older. So this looks like it's doing something with the number of deaths for certain ages. And rather than do 85 to the next upper limit, they just decided to do 85 and older. When data are discrete, we can construct a frequency distribution in which each possible value of the variable forms a class. The following table and histogram presents the results of a hypothetical survey in which 1,000 adult women were asked how many children they had. Notice 0 children, 435 adult women had no children. So that's right here, 435. This one goes up to 175. This is approximately 222. This one's approximately 112. So again, I'm just reading off of these values for the number of children on each line. This is with the frequency, not relative frequency. If I wanted relative frequency, I would have to add these all up. I know they're already 1,000, but that's a good double check. And the relative frequency of the first one would be 435 divided by 1,000. The relative frequency of this one would be 175 divided by 1,000. But they're not asking for those numbers on this particular one. The shape of a data set. A histogram gives a visual impression of the shape of a data set. Statisticians have developed terminology to describe some of the commonly observed shapes. A histogram is symmetric if its right half is a mirror image of the left half. There are very few histograms that are perfectly symmetric, but many are approximately symmetric. Notice when you're looking at this picture, if I drew an imaginary line down the middle, the right half looks relatively the same as the left half. A histogram with a long right tail is said to be skewed to the right or positively skewed. Notice how this has a tail to the right? That's positively skewed or skewed to the right. So you look at the tail when you talk about skewing, not the peak. A histogram with a long left tail, right here, is skewed to the left or negatively skewed. A peak or high point of a histogram is referred to as a mode. A histogram is unimodal if it has only one mode. This only has one high point, so that's unimodal. And it's bimodal if it has two clearly distinct points. An ogive curve is constructed by plotting a point for each class. The x-coordinate of the point is the upper class limit and the y-coordinate is the cumulative frequency. Then all the points are connected with straight lines. Notice how we have the right here, the 0.99. This is the upper class limit and the cumulative frequency. So for this upper class limit, we plot a 9. For 1.99, we plot a 35. For 2.99, we plot a 46, etc. And finally, to get to 65, notice that this ogive curve is an increasing curve.